Welcome to Study Loop.
Okay, so our question states that an object which is at the origin at time t equals 0 has a velocity v naught equal to minus 14 I hat minus 7 j hat meters per second, and an acceleration vector equal to 6.0 I hat plus 3.0 j hat meters per square second. And then it wants you to find the position vector r where the object comes to rest momentarily. Okay, so I wrote down what we were given here. We were given that the initial position is at the origin. So r of 0 here is equal to 0 for all components. V of 0, our initial velocity, is equal to minus 14 I hat minus 17 j hat meters per second. Or I'm sorry, not minus 17, it's minus 7. So let me erase that 1 there. So it's minus 7 j hat meters per second. And then A is equal to 6.0 I hat plus 3.0 j hat meters per second squared. Okay, so before we begin solving this problem, we notice that the position vector can be found from equation 3-13b since the acceleration vector is constant. And the time at which the object is going to come to rest is found by setting the velocity vector equal to 0. Both components of the velocity vector must be equal to 0 at the same time for the object to be at rest. Okay. So first thing we're going to do is we're going to write the value of the velocity vector. So v here is equal to v naught plus the acceleration vector times the time. Okay. Well, this is equal to v naught, which is minus 14.0 I hat minus 7.0 j hat. Okay. And then that's going to be added to the acceleration, which is 6.0 I hat plus 3.0 j hat. And that's going to be multiplied by the time. Now, the object is at rest momentarily when both v of x, so the x component, is equal to 0, and v of y is equal to 0. Okay, but the x component, v of x, is minus 14 I hat plus 6 I hat times the time. So you have 0 is equal to minus 14, because this is the x component, so we'll write this x out to the side. So this is the x component. Okay. It's 0 is equal to minus 14 plus 6, right, times the time. And this is the maximum time for the x, so we'll just mark this as mx. If you solve for that, you get t mx is equal to, it's going to be 14, right, divided by 6.0, that's seconds. So this equals 7/3 seconds. Okay. And now for the y part, well, same thing. It's equal to 0 at maximum. Okay. So that means 0 is equal to the y point part, which is minus 7.0 for the j hat, plus 3.0 times the time. But this one is t maximum in the y. So we'll do t my for t maximum in the y. Solve for t maximum in the y. And you get the ratio of, again, 7/3 seconds. So they're the same. So clearly it's at rest momentarily when the time is equal to 7/3. Okay, now that we know it's at rest momentarily when the time is equal to 7/3, we can use our equation here to find the position vector r, which is r naught plus v naught of t, or v naught times t, plus 1/2 a times t squared. Well, t is equal to 7/3 seconds here. Okay. And we also, now we just need to plug in our values for v naught and a, which are on the previous page here. V naught is minus 14 I hat minus 7 j hat. Well, we also need to plug in our value for r naught, but that's just 0, so we can ignore that. So minus 14 I hat minus 7 j hat times the time, which is 7/3. Okay, plus 1/2, and then the acceleration, which is, let's see here. If we go back to the first page, is 6 I hat plus 3 j hat. Okay. And this is multiplied by the time squared, so this is 7/3 squared. Okay, and if you want to put parentheses around all of this and denote this as meters, that's a good idea. Oops, let's draw a better M, because that is the units of the position vector. Okay, so now if you go through and you carry out all the multiplication, so you do minus 14 times 7/3 I hat plus 1/2 times 6 times 7/3 squared I hat. That's going to give you minus 16.3 I hat. Okay. Now we want to find j hat, so you have negative 7 j hat times 7/3 plus 1/2 3 j hat times 7/3 squared. That's going to give you minus 8.2 j hat. Okay. And the units on this are meters. So we go ahead and box this in, and that's our solution.